Hi, this video we are going to look at the Webwork HW3P2 problem 2. So this is a stress problem, and it's a very cool project or slash problem here. This is 3 components assembly. You have this Clevis, like U-shaped components here, and then you have carved a circle on top and the bottom flange, and then you have a pin going through, and in the middle there's a tongue. Okay, and we have external force, one to the left, one on the right, and they balance each other. So they give us all the dimensions here. They also give us a bunch of things here, the stress. Because it is made of 3 different materials for pin, tongue, and clevis, and each material itself will have 2 stresses, one for normal, one for shear. So as you can see, there are a total of 2 times 3 stress properties. So in order to have a very clear mind, I will go ahead write down them mathematically. For example, for normal stress in the pen, I'll use sigma. That's this value. Then shear stress, which is our tau, right? And I'm going to write that's tau, and it's also pen. And then the third one, it's normal stress in tau, so it's sigma. Then the fourth one, it's a shear again, so it's tau, but this time it's not pen, it's tongue. Then the last is clevis, and clevis have sigma, normal stress. And then we also have tau for the last one for shear, right? So those are the few things here. I can even go ahead and put my values here. That just help me solve the problem later. And they all have the unit of megapascal. Okay, so I encourage you to do the same. So now the first problem is A, that corresponding to this question, assembly fails due to the pen sharing. Okay, so the best way to solve this is actually thinking about a couple of things. The first one is the pen. If we were trying to isolate the pen out, and it has to be shear. So if I were to draw this top clevis, and here is our bottom one. And the pen, that's what we're interested in. It's right here, right, curved right here. And we have external force F to the left because I'm just only looking at the left. So I have this pen going through right here. And like we said, it's going to be pen sharing. Sharing is going to be parallel. To parallel to this force will have to be lateral, left and right. So at the pen will have to be this black surface right here. And there are 2, top and the bottom. And then this is one shear, and there's another shear, V. So in that situation, you identify 2 things. First thing is this shear is going to be equal to F/2 for each one of them. So if I were looking at one of the force, F/2, that corresponding to that only one surface area right here. And this is a circle with, if I were to draw this area, it's basically the circle and with the diameter of D. So in that, it's pi d squared over 4. Okay? Or what you could write is, said, okay, I'm going to consider these 2 shear force together. Then they have to be equal to this external force F. And however, now I have two surfaces, right? So basically two circles. And two circles, that will be pi d squared over 4 times 2. In that situation, those two equations basically the same, right? Okay, so then they both gonna be equal to what? This is shear force over the area. So that's going to be equal to the shear stress. So that's going to be tau of this subject, which is our pen. And for this situation, it's 280 megapascal. Now let's think about the unit. You notice all the dimension here is millimeter. We talked about in the previous video. If force unit is Newton, and area, if it's millimeter square. So basically, dimension is in millimeter, which is for this problem. Then, what do we get? Millimeter is going to be 10 to the negative 3 meter and square. And then you have a Newton, 10 to the negative 6 meter square. And flip that up, that's 10 to the power of 6 Newton meter square. That's basically 10 to 6 Pascal. And that is our megapascal. So this makes things really easy for us, knowing that, because if I get megapascal and I'm using the dimension here using millimeter, then I am destined to get my force in Newton, right? I'm going to get that. So in order to solve this equation, so F is going to be equal to 2, I'm going to use this, 2 pi d squared times 4, then times 280. That's going to be my answer for that. Go ahead, pause for a second, see what you got for this. So here is my answer. I got F has 98960 Newton. So that's the first answer right here, 98960 Newton. That is the force that's going to be maximum force I need to prevent my pen right here being sharing. So that's the first problem, okay? Now let's look at the second one. The second one is assembly failed due to the tear out of the tongue. So let's look at it. So tongue is right here, this rectangle prism, and it's tearing out. So if I were going to draw my tongue out, so this is the tongue, and when we isolate that out, we know there's external force F to the right, and again there is a pen going through, so there's a circle. It's tearing out. Thinking about the motion, if this tongue gonna be tearing out, they are going to go through this path. It's going to turn out right there and right here. Then if we were trying to draw that, you were going to be thinking about this is going to be the first surface, and you're going to have exactly the same surface to the inside. So what you will have, you will basically have this rectangle if we were taking it out. And this tearing out with respect to this surface is going to be parallel. So that's going to be your shear. So on both of them, it's going to be shear. And each of them will be equal to F over 2. And then if you look at one rectangle, let's look at the dimension. What's the dimension right here? So let's go back to look at it. The dimension right here is going to be B. And the height is going to be basically the depth of the pen that is inside of the tongue, which happen to be your T. Okay, so in that situation, if you were looking at, if I were trying to draw, so this is going to be this first, the inner surface, and then you have another surface. They both going to be counteract this external force. So knowing that, we already know the shear force is going to be F over 2 for each of the surface, And each of the surface is going to have the area of B times T. And again, this is a share. And it's a share, so it's a tau. And this is the tear out of the town, right? So we're looking at the town, sharing out. And let's go back to look at what we have. It's 637. Oh, I'm so sorry. This is a pen. Oh no, tearing out of the town. Okay, tearing out of the town. It is the, I'm so sorry. It's this one, 286. Okay, it's 286. So knowing that, go ahead. You can solve your F. F is gonna be 286 times your B times your T and times 2. And my B and the T are 20 and 11 respectively. So put all those in there, we can solve our force. That is 125,840 Newton. So go ahead and pause to check the calculation. So this is basically the maximum force that is allowed to prevent this town being tearing out. Again, this tearing out is going to be shear, right? Thinking about it, it's going to be parallel to those two surfaces. All right, so let's look at the problem C. It is assembly due to tear out of a clevis. All right, so clevis is this U shape. So if we were trying to go ahead, draw out this U-shape clevis, what do we have? All right, it will be something like that, right? Again, you have this pen on the top and the bottom. And now we're going to look at this external force to the left. So basically, this force right here. And if this will be tearing out, you think about it, it's going to turn out, the clevis is going to be along this edge. Not only top, and you have mirrored same image at the bottom. So potentially, you're going to have what? You're going to have 4 identical rectangles. So those is going to be the surface area that's parallel to the force. There are 4 of them. So if I were to translate it here, what we would have, it's going to be this first. So that's going to be top and the bottom. So there are a total of 4 of this surface area. Okay, and now let's look at the dimension for this surface area. And what is going to be the depth there? The depth there is going to be this value. That's going to be your C. And what is the tear out path? Basically from here to here. And that's giving us as A. So it's A. Okay, so those 4 surfaces, they are going to be identical, and they are also going to have identical forces, which is going to be F over 4. And that's your share. But in order to solve this problem in one simple step, I could say, okay, all those 4 shear forces together have to counterbalance this F. So that's going to be F. And then, however, it's going to be 4 surfaces, right? So in that situation, I'm going to have 4 times A times C. Or you can say, how about we look at one individual rectangle area? Sure, we can. Each one is F over 4, and each one of the surface will be A times C. And you notice that they're the same. All right, so that's going to be equal to share against tau, but this time it's going to be clevis. And our tau for clevis is 492. Write this value. Then go ahead and we can solve this F. F is going to be 4 times A. A for mine is 19. And C is 7. So 4 times 19 times 7, then times 492. Did I get this right? Tau for, oh, I'm sorry, I keep on getting the wrong value. Tau for share is 196. Oops, 196. So here is 196. So go ahead and solve that. We'll get 104.272 Newton. Okay. All right, so that's the first three. Now let's move on. By the way, what does value mean? That's a maximum force allowed to prevent this clevis being torn out. Basically, reach up its maximum shear stress. Now, let's look at problem 4. They said the assembly fails due to tensile failure of the town. Tensile, that's going to be normal now, right? So the first 3, you notice it's all shear. Now let's look at the tensile failure of the town. Town is this one right here, the rectangular prism. And we're going to consider this is going to have a normal stress, normal force. So first of all, we go ahead and draw the town. Okay, and then again, remember this town is subjected to this external force. And again, you have 2 carved circle, one on the top, on the bottom. And this time, we're talking about normal. Okay, the normal, the failure due to tensile of the town. So tensile, normal, have to be perpendicular to these forces. In order to make it perpendicular, then the first thing you can think about, and it have to be inside the town, so it will be here. Those 2 identical rectangles, they are going to have force identical, and that's normal force. And they are both equal to F over 2. So if we were trying to dimension this rectangle, let's look at it. What's the thickness of the town? The thickness of the town is T. So let's translate this to be T. And how about the dimension here? So in order to solve this one simple way, I can just say those 2 combined normal force have to be equal to this force. So that's going to be F over this combined surface area. So it's going to be rectangle. So it's going to be this surface plus that surface. And this is T. How about those 2 surface top add together? We know what's the dimension for this dimension. This dimension is W. And we know the pin has D being a diameter. So translate over here. So that's going to be a W, and this is going to be the D. So knowing that, all those together, this and plus that is going to be W minus D. Okay? So knowing that, so you put 2 rectangles together, add up together, it's a big rectangle. So the dimension is W minus D times T. Then this is going to be, again, it's normal. So it's sigma. And now we are looking at, this is 10. Now go back to look at sigma 10 is 637. So put that in as 637 and put the dimension for W. My W is 42 and my D is 15. All this together, then times the thickness is being 11. So put all those, we calculate our force is being 189.1 interesting number. So that's my force, and that means this is a maximum force allowed to prevent the tongue having a tensile breaking down, right? Being broken on this surface here. Because what do we consider about this surface? You said, oh, why couldn't we consider this surface? Yeah, that's also perpendicular to this surface. However, this has way bigger of area. If this tongue is gonna break due to tensile, it's gonna break at the minimum surface, right? And minimum surface is when the circle, when the cylinder of the pen is carved out there. So it's gonna be those two areas. Okay. Now let's look at problem 5. Problem 5, it fails due to tensile failure of Clevis. So Clevis is going to be that U-shaped one. And now we're going to, in order to do that, we go ahead and draw the Clevis so we can think about it. So this is our Clevis. Okay. Again, our pen going through them. The external force this time is going to be to the left force. It's going to be the tensile stress at the Clevis, so that will have to be perpendicular. Again, perpendicular to this force will be at this dimension, and this dimension at the minimum area, it's where the pen is carved out. So go ahead and draw that. We'll have this surface, then we'll have the other surface, left and right, symmetrical on the top. Then, do you agree we're going to have the same mirrored surface at the bottom, right? And then we'll have 4 identical force here to balance this, so they all equal to F over 4. Or you could say, altogether, write down our equation. It's entire normal force combine those 4 rectangle area together is F. So we need to combine all those rectangle together, right? So if you think about it, what is going to be the thickness basically here and here? Let me use a different here and here. So let's go back to look at the geometry. It's going to be C for each one of them. So C. And now let's thinking about this. This is very similar to problem 4 we have over here. How about we consider this dimension and that dimension together, right? So let's look at the Clevis. The entire length is W, and then minus the D. So in that situation, all this together will be W minus D. And this is 2C when you add those two together. So all the 4 rectangle area add together, or it's going to be a big conglomerate of this rectangle. It's going to be W minus D times 2C. That's normal. So normal is going to be sigma, and we are looking at 10. And let's go back to look at the 10, and we have 6. Oh, I'm so sorry. This is not 10, this is Clevis. All right, got to get mine clear, right? So Clevis 10 it's gonna be 492. That's 492. Put all together, plug all values, dimensions in. My W is W42, D is 15, and then times 2, then times C, thickness is 17. Look, 7. C is 7, right? Let's just double check. Yeah. Then all this together is going to be equal to 492. Then that will help us to get our force calculation is 185,976 Newton. All right, so we finish 5. Okay, so now let's look at the next one. So what do we get? The next one is called this. What does that mean? It's a sampling failed due to the bearing stress between the tongue and the pen. Okay, so we never talk about bearing stress. So in a nutshell, bearing stress is basically normal stress. And bearing stress is when two materials are contact together. For this instance, you have this pen and a tongue contact together, and it has to be normal. Okay, so in order to do that, we're going to draw, knowing that we're going to draw our tongue and this pen, and we have the external force F here. Remember, this have to be bearing stress. Bearing stress have to be normal, so have to be perpendicular to this force. Perpendicular, then we'll have this. Maybe I should draw better. Yeah, that's better. So it's gonna be this. That's gonna be the surface that's perpendicular to this force. So that's gonna give us also F. That's your normal force. And this surface is going to be diameter D for this dimension, and this is thickness, that's a T. So knowing that the bearing stress we are solving is going to be force, normal stress over dimension, D times T. And here is, since there are two materials, one is tongue and it's normal and another material is the pen. So which one do we use? Here is simple logic. We're going to use the minimum, right? If something is going to break with those two materials contact due to the normal stress, it's going to break at a weaker material. So you're going to use the minimum one, always choosing the weaker material. Now let's go back to look at for this problem. The tongue and the pen for normal for pen 701, and for tongue is 286. So obviously we're going to choose the small one. That's 286, and that's our logic here. We're going to use 286. Okay. We're solving 6. I'm just trying to be clear. Let me see, go back. The 6, oh, it's tongue. Yeah, okay. So we're using 286. Sorry, I made a mistake. I'm getting the share. So it's not 286. For tongue is 637 compared to share normal stress for pen 701. So we're going to use 637. Okay. So now we're going to put our dimension there. Our D is 15, the diameter of the pen, and the T is the pen that's going through, and that's 11 right here. And that's going to give us 637. Then from here, we can solve our force in that situation. What do we get? We get 105, 105. Another interesting number. All right, so let's look at the next one. They're asking about the bearing stress due to fails between Clevis and the pen. So it's very similar to problem 6, but now we are not looking at 10, we are looking at the Clevis. So if we were trying to draw the Clevis right here, okay, then again, you have circles, and we have external force F going to the left, and this is bearing stress. Bearing stress is going to be the contact area, so it will be right here. Contact. So only contact is going to be this top surface and also this bottom surface, right? We're not going to look at the middle because they are not in contact. So knowing that, we're going to think about this geometry. This is going to be C. That's a thickness there. And this is D, again, diameter of the pen. So knowing that each of them is going to be half F over 2, that's going to be normal. So force over 1 force over 1 area. This 1 area will be D times C. Again, this is bearing stress involved 2 materials. As you already speculate, we're going to use the normal stress for the Clevis and normal stress for pen, the small one. Go back here, hopefully I don't make a mistake. So the normal stress for pen is 710, and for the tongue is 637, but we're looking at Clevis. The Clevis is going to be 492. So we're going to use 492 for this. Okay, so put our values in. So F over 2, our D is 15 millimeter. Our C here is 7. All those together equal to 492. Then put all those value there. You can solve for force. That's 10, 33, 20 Newton. So what does this value mean? This value mean if you're not going to have this contact area, which is bearing stress, to fall off, then we're going to have maximum force of this value. Okay. So very last one is asking overall allowable. What do you think? You got how many numbers so far? A, B, C, D, E, F, G. My goodness, you got 7. So all those are maximum number to prevent something happen and to avoid some kind of engineering disasters. You want to have this overall allowable to be what? The minimum of all the numbers you find out. The top 7 numbers you find out. Then that's the answer. All right, so hopefully this was informational and that give us an idea how to approach a problem like this. All right, I'll see you next time. Bye.